Good morning, everyone. Welcome back to lecture number 6 of the Probabilistic Machine Learning course. I'm happy to see that many of you are still here. I think I've seen a few faces that are now missing and a few new ones. That's good. It's good that there's still new ones for sure. Here is the feedback from last week, which was a lot better than the one before. So I'm happy that I've caught up with many of you again with this slower lecture on regression. So the number of people giving feedback is now pretty constant. I think we've sort of reached saturation or steady state. And overall, you gave very positive feedback, which is why I will do this here very quickly. Someone pointed out that my colleague Matthias Hein uploads his slide as in a bulk. And so sometimes the stuff that I look at in the slides may not be what he's currently doing. Did he do least squares regression today? Because those are the slides he uploaded. Ah, very good. Then I can skip one step ahead of him and prepare you for what he's going to be doing in his next lecture. I also spoke with him and heard that he might actually come and he might move his lecture here to this room if he's able to. That's good. Then you can stay here and don't have to walk across the street anymore. And then maybe at some point in June we can all move up together onto the Neue Viehweide. A lot of you liked the coding example, which is perhaps not surprising. The sort of extensive examples, I've cut out a few comments here. Several people said you like the example. And then there are 3 questions here at the end. Let me see if I will pick out the first and the last one. The first one is a question about how do we scale, how do we calibrate the uncertainty of the probabilistic model in the light of data to make sure that these error bars that we're constructing actually mean something. It's a very good question and maybe something to just point out that this is a problem I haven't fully addressed yet. I've just told you how to compute posterior uncertainty, but so far I've actually said very little about whether you can trust this posterior uncertainty or what it means, in which sense to really interpret it as an error estimate. We will have to work on that in the lecture. Actually, it'll take another week or so till we get to that point, because it's actually not non-trivial. So if you are wondering why you should trust these error bars, that's a very good question. You have exactly the right intuition. And someone said, well, this last part about the linear algebra was maybe a little bit rushed. I agree, actually. I would have loved to do like 3 more lectures on numerical linear algebra, but then we would have to leave out other things. So there's always a bit of this trade-off between me doing a few things that I'm particularly excited about and also focusing on some stuff that I feel you probably want to hear anyway. And so I'll sometimes have to balance this a bit, do some content a bit faster than you might want to create time to do some other content that you may actually want to see as well. Then there are also repeatedly, again, questions on the forum, on Ilias, in person here up front to me about literature. So where can you read up on this? And here, I mean, I'm repeating myself, I realize, but I want to be, I'll just say it again, basically, right? Because I want to be clear on this. So there are, of course, textbooks on machine learning. And I could make a longer list here. A particularly good one for the current part of the lecture, not for the whole course, but for these few lectures that we're currently doing, is this wonderful book by Carl Rasmussen and Chris Williams, which is available for free online as a PDF. It's the defining textbook for Gaussian process regression in machine learning. It was written in 2006, actually here in Tübingen, when Carl Rasmussen was an Emminuter group leader here in Tübingen at the Max Planck Institute, together with Chris Williams, who was at Edinburgh at the time and still is. It's a great book, but it's from 2006. And actually, I know that Carl has been working on the upgraded version 2 of it for a long time. I don't know when it's going to come out. So some of the stuff in there is a little bit dated. It's MATLAB code. You know, it's maybe not exactly in the sort of the style that we're used to in machine learning these days. I say MATLAB, people smirk, but in 2006, MATLAB was absolutely state of the art and Python was complete crap. So the other book, of course, that I shamelessly will have to promote here is my own one, which is also available for free online, where you can read a lot more about the numerical linear algebra questions. But again, I don't want to tell you to read the chapters there on numerical linear algebra because they're quite dense and deep and sort of on a level for PhD students maybe who really want to get deeply into this stuff. You can also just read the papers that I keep linking on the slides. So your master students now, at least most of you supposedly are, you can read primary sources, and if you want to do machine learning, you have to get used to reading primary sources anyway, because, and that's my main point again, there really aren't any good textbooks at the moment. There are some dated ones from 2006 that are great for their time. There are really some wonderful, great books out there. Chris Bishop wrote a great book in 2007 as well. David McKay wrote one of the most amazing textbooks on information theory and learning in 2001. I very much recommend that you have a look, but it's from 2001, and there's 24 years in between when an entire field emerged and built new stuff that isn't covered by these classic books, although they're very well done. And then there are more recent books, and I'm not going to name any names because I'm going to be a little bit critical of them, that came out more recently, or actually maybe I can. So Kevin Murphy, for example, has a textbook on probabilistic machine learning. That's probably the most recent book and the most complete one that covers most of machine learning. And when you read it, it's also available for free online as a PDF, you will notice that, understandably, Kevin had to be very quick in writing it. And so you'll see that the content is often just, it seems a bit rushed. It was written by many different people. He had individual people helping him, writing some Jupyter notebooks that don't quite fit into the notation of his textbook. Some things feel like they've just been shoehorned in and were written by people who didn't even know that there are other parts of the book being written at the same time. And so they don't really make like for a nice story arc. And that's okay, right? Because at this point in the field, everything is moving so fast that it's impossible for anyone to keep track of everything, even though Kevin has been doing this Herculean effort to stay on top of stuff. And as a result, by the way, there's a meta point here, which is maybe very, like something for you also to reflect on. At the moment, there is no consensus in the field on what the canon of machine learning is. If you're studying, I don't know, bioinformatics or mathematics or physics, most people in the world agree on what a physicist should know when they get their masters. There's like, old textbooks from 1945 that basically cover most of the important stuff, or maybe from 1970. In machine learning, that's not true. And if you go to workshops with colleagues my age and younger, people wildly disagree on what you are supposed to know. So what you are learning here is quite different from what you would be learning in Zurich, in Munich, in Cambridge, in Stanford, or in Toronto. But that doesn't mean that the other places are going to teach you more or less, just different stuff. So we're taking quite a concrete decision to focus on some things, and that's actually why I think that's a core value of this machine learning master's degree here at Tübingen, why you have these two classes happening at the same time, or well, at the same point in the semester, right? By Matthias Hein and myself, so that you get to see two different ways of stressing certain parts, leaving out some other parts. And I hope that you're taking this opportunity to also reflect on the fact that the people teaching you this stuff don't necessarily know exactly what you should focus on most, or what should be the most important one. We probably know more about the field than you do, because we have the advantage of a few more decades of research, so we can pick out a few things. But I can assure you, other colleagues of mine would focus on other stuff. As a matter of fact, I had a conversation, not just with Kevin Murphy, but with various other people in Dagstuhl last November about what we should actually be teaching in machine learning these days. And there was, like, if there were n people in the room, there were n+1 opinions about what to focus on. And I showed them actually a list of the stuff that I'm going to do in my course here this term. And there was a wide mix of, what, you're doing this? How do you get all of this into this format? Why are you not teaching this? Why are you not doing this? Are you covering causality? Are you doing variational inference? Why are you not doing, and yeah. So at the very end of the course, I can maybe do a bit of an outlook of all the things that we didn't do and could have done if we had more time. So with that, let's get back to our main question. So last Thursday, we spoke about regression in a very basic, hands-on fashion. We constructed an algorithm that loads individual data points or linear combinations of data points from a data set to learn a functional relationship between inputs and outputs. And we did that by leveraging the algebraic structure, the algebraic powers of, let's call it the Gaussian mechanism. This thing, these algebraic properties of basically quadratic functions. I mean, that's what we're literally using, right? The fact that quadratic functions are closed under all sorts of interesting operations, like parabolas, state parabolas. If you cut through them and if you marginalize them, you project them, and so on. And we translated this into a language for doing inference in the Bayesian framework using Gaussian distributions under linear maps that effectively create linear algebra problems. And then the second cool step was to say, we can take a finite dimensional Gaussian distribution over parameters W, over weights, and turn them into a distribution over functions by mapping these weights out onto feature functions. So we create functions, classes of functions, that are finite sums over basis functions. A parametric model, this is called, because it explicitly uses parameters, W. And we realized at the very end of the lecture that you basically get to pick what these features are completely freely. It's sort of tempting to think of some special features, like the Fourier basis, or the polynomial basis, or some other kind of interesting basis of some function spaces. But for a concrete regression problem, and we will do a concrete example, I think next Tuesday, maybe, you will see that it's certainly not necessary, or maybe not the most natural thing, to pick some generic basis class of functions. Instead, you could also use these crazy features that I sort of, some of which I introduced, like step features and VLUs and various weird polynomials that you could collect, or something else that you like, some piecewise linear, non-continuous, whatever functions. So the mechanism for this we had in forms of code, in forms of pictures, and in form of this massive piece of math that I'm going to throw at you again. So if you try to write down the entire thing we did onto like a slide, then let me remind you, just to sort of get you into the mood again, what we're doing is we're trying to learn a function that takes inputs and maps them to outputs. And we're writing this function. Actually, I could write this as, if you like, sort of a second order function of inputs, x, and weights, w. But I'm just going to omit the weights here in this notation, but they're still there. Now, because I'm omitting it actually because I want to treat these weights separately as something I want to be uncertain about, and then I want to integrate it out. I want to integrate out this variable that I don't know, right? So I want to learn about it from data and then get rid of it. So to do that, I put a probability distribution over these latent quantities that I don't know, and I cunningly choose that distribution to be a Gaussian distribution because I know that Gaussians have great properties. Gaussians have two parameters, a mean and a covariance. And the second key assumption I make is that the observation likelihood, the likelihood for the data that I'm going to see, the outputs y, is itself a Gaussian distribution over the data y. This is not a Gaussian distribution of the inputs x. Let's just be clear about that. It depends on x in some arbitrary fashion because we get to pick the features in any way we like. But we don't care because we assume that we know what the inputs are when we do the computation. It's arguably also a Gaussian distribution of the parameters w, but sort of indirectly, right? The distribution, it's only an incomplete or a singular distribution in the weights, but that doesn't matter because it's a likelihood, and likelihoods don't have to be probability distributions in their right-hand side. So then we do inference. There's only one way to do inference. It's called Bayes' theorem. We multiply the prior by the likelihood. And for Gaussians, with linear relationships between data and latent variable, it turns out that the posterior distribution is then itself a Gaussian distribution with new parameters, new mean and covariance. And those new parameters, they come at us in these sort of ugly expressions that we've now been staring at for so long that we actually maybe don't find them so ugly anymore. So what we see here is that the posterior mean, this new updated point estimate for what the parameters of our function may be, is the old estimate before we saw the data, plus a correction term, which is actually best read from right to left. We take the data, we compute what we would have predicted the data to be, that gives us a residual, then we scale by the variance of the data, so that's kind of the scale on which we expect this thing to vary. And then we project back out into the space of the weights And this is actually, this term that shows up here, it happens to be the covariance between the weights and the data, and therefore sort of connects between data and weights. And the posterior covariance, the uncertainty that we find here, is equal to the prior uncertainty, so that's a large thing, minus something because we've learned something, we've become more confident. And this term, actually, as it happens, so this is just a property of inverses of matrices. It's not particularly intuitive why it looks this way. It's the Schur complement, if you really like, but the Schur complement is some kind of group theoretic property, so it's a little bit difficult to get an intuition for why it looks the way it does. That this term, the most important thing about this term is that it's the same matrix inverse that we also needed in the mean. This is nice from a computational perspective because it means that we can do one computation once and reuse the computational effort to also get uncertainty. And we're back. So we can reuse computation. Okay, now before I lose you, now the final step is that we can take this distribution over weights and easily turn it again into a distribution over functions by taking this Gaussian, by realizing that our function is a linear map of the weights through these feature functions, which are nonlinear functions of the input, but they create matrices that are linear maps of the weights, and create a distribution over function values by basically just multiplying these feature functions of wherever we want to evaluate to the left-hand side of the mean and from the left and the right to the covariance using a property of Gaussian distributions. So before we move on to do more with this framework, I want to point out an extremely important connection that hopefully motivates you to keep thinking about this particular framework. Namely, that what we've built here is a neural network, but a shallow one, not a deep one. So how does this work? So let's think about what we are actually here computing. So for a moment, let's sort of, step outside of the Bayesian framework and see what we're actually sort of mathematically, numerically doing. So we're computing this posterior distribution over the weights, this P of W, given the data, y and x. And we do that by using Bayes' theorem. So Bayes' theorem says that we should multiply the prior over the weights by the likelihood for the data, the likelihood for the weights as a function of the data, divided by the evidence. So what we could do is, first of all, let's think about where the mode of this distribution is, where the most likely estimate for W lies. How would you do that? Well, to make your life easier, this is a common trick that we're going to be doing a lot over the course of this term. We're going to take the logarithm of the probability distribution. Why is that? Well, probabilities are always positive numbers, so you can take the logarithm, and they tend to be related to something exponential of some interesting function, like Gaussians are the exponential of a quadratic. In fact, we'll get to think a lot more about this structure in a few weeks. There's a lot more to it, but let's stick with it for a moment. So if we take the logarithm, we just get rid of the exponential, and we're left with the business end of the distribution, which also simplifies Bayes' theorem, because now the negative logarithm of this thing is the sum of the negative logarithms of prior and likelihood plus the evidence. So many interesting things happen here. First of all, the evidence becomes a constant. It doesn't depend on the weights, so we don't have to care about it anymore. We just shove it out. It doesn't shift the location of the maximum. It just raises the function up and down. The second thing is I've put a minus in front because now we can think about minimizing this function, which is just the normal notation that people use in optimization, right? So people like to minimize somehow instead of maximize. Other than that, the minus doesn't matter at all. So if we now think about what this logarithm of likelihood and prior actually is, you'll find that, so think of a Gaussian is the exponential of a square. So our product over individual Gaussian likelihoods is a sum in the logarithm over individual quadratic terms between the data and feature functions times weights. And the prior over the weights, well, that's a quadratic form. So an inner product between a vector shifted by the mean over the weights and itself scaled by the prior covariance. So this has the shape of an empirical risk function plus a regularizer in the weights. So for those of you following Matthias Hein's class, I hope you're making the connection. Right? A regularizer is something that doesn't depend on the data, only on the parameters. An empirical risk function is a sum over individual terms, where each term in the sum depends on one datum and all the parameters. And we're maximizing this thing. So let's think about what we do when we find the mode. We could compute the gradient. In fact, we could train these models with gradient descent if you like. I mean, I invite you to try this out yourself. You can absolutely use your favorite stochastic optimizer, stochastic gradient descent, Adam, Madam, Nadam, Sadam, whatever, right? And follow this gradient, which I've here computed analytically, but of course you could also use autodiff to do that for you. It's just a quadratic loss, an L2 loss, if you like that notation from deep learning. And we're getting a gradient which interestingly depends linearly on the weights. And a gradient of the regularizer that also depends linearly on the weights. That's maybe not surprising, right? Because if you have a quadratic function, you take the gradient, you get something linear. The gradient of a square is just a linear thing. Which is nice because that means we can rearrange the terms into matrix times linear term plus constant, and then we can solve for this analytically using a matrix inverse. Not surprising because we've already been doing it. What we find is the mode of the distribution, which is actually equal to the posterior mean that we've computed so far. Also not surprising, right? Because Gaussians are bells, so the mode is equal to the mean for Gaussian distributions. So our posterior mean, our point estimate, is the minimizer of the empirical risk function. And the posterior covariance actually also has interpretation. You can convince yourself that if you take the second derivative of this thing again, oh, there's a mistake here. Can someone see the mistake? There's an inverse missing. Whoop, whoop, whoop. So the precision matrix, so brackets around this with a minus, there we go, is the second derivative of this function. No, it was right before. No, I've added the, okay, that's the danger of correcting things as we go. So it's good, I don't have to upload a new set of slides. So the curvature of the loss is equal to the inverse covariance, the precision of our estimate. Makes sense? If you have high curvature, you're confident, you have high precision. If you have low curvature, you're unconfident, you have high uncertainty. So these two quantities that I've derived as Bayesian properties, as mean and covariance, you can also think of them as describing the geometry of a loss landscape. A loss landscape that has constant curvature, so we are in a Euclidean world, if you like and think about stuff in a geometric sense. And we have a gradient that always points in this parabola towards the point estimate, the minimum, that is equal to the posterior mean. So in the Gaussian language, we can do Bayesian inference by minimizing empirical risk functionals. And we've done this with these specific feature functions where I sort of say, well, you can pick whatever feature functions you like, sines and cosines, but we started out the story at the very beginning by saying, oh, maybe one set of features could just be the linear features, right? So phi of x is just x. So it's literally just phi of x is equal to x. That's the most trivial choice you could make. Then you're learning a linear function, even without intercept, right? So then, if you think about this, then the terms that you would get here, just mentally replace every phi of x with x. And now you can do another thing. You set the prior mean to 0. Okay? If you set the prior mean to 0, which is maybe like a standard choice, then this drops out, this term. And the second thing you could do is you could say, maybe I'm maximally uncertain. I really don't know anything about the data at first, about the parameters at first. So my sigma inverse goes to 0. Right? Sigma goes to infinity, sigma 0 goes to 0. Then we have zero precision. We don't know anything. It's dangerous to do that because it might break this matrix here and make this inverse ill-defined. And then everything is going to be a bit nasty. But, you know, let's just try it. OK, so if we think of this as 0 and this as 0, then this sigma cancels. And what are we left with? We're left with x transpose inverse times x times phi. And on Thursday, these are the slides by Matthias Hein that I just downloaded. He's dangerously already uploaded to his Moodle, even though he's not done that yet in the lecture. You're going to see him on slide 6, introduce least squares regression. And there you see the exact same expression, right? So that's the corner case of what we've done so far. And what is he saying down there, where the inverse exists, that are important? Never compute the inverse, but instead solve using a linear, solve the linear system. This is much more computationally efficient and stable. He's just going to say that, and then you say like, yeah, but Hennig has already told us about all of that. You know? Huh? And then you can be like, okay, good, I can go faster. Yeah. And then in his lectures, he will talk, actually on the next slide, he says, this is ordinary least squares, and then maybe a little bit later he says, you can also pick features, right? That's the outlook into his lecture. He's like, we can pick features, and then this could also be a pre-trained neural network. Good point, actually. Yeah, of course, you can also take whatever features you've already learned with the network. And then you'll find that, you'll do the exact same thing. You'll find a notation again that I've introduced, this nasty one, but now you're going to be super confident and tell Matthias, yeah, this is also easy. And then at some point, he will probably tell you that we need to regularize because otherwise things get unstable. If you don't have as much data as you have parameters, things are going to fall apart, right? The matrix is not going to be invertible. We'll do something nasty. So we should regularize. How do we do that? Well, we introduce a regularizer for our weights. And now you know that that's a Gaussian prior. And what he's computing, even though he calls it rich regression, is a posterior mean estimate from a Gaussian. And then you can ask him, what about the curvature of this problem? Isn't this somehow interesting as a quantity? And he'll be like, what, curvature? No. Okay, so here we go. And so I'll leave it at that. Enough making fun of my esteemed colleague. So what we're doing here is also, by the way, learning a neural network, right? So what you see here is an input. We're computing a bunch of features. And then we're inferring the weights for the output. So for those of you thinking along in deep learning terms, you know that this here could be features that you've learned in some other way using deep learning. That's why it's called deep, because it happens underneath the stuff that you would otherwise do. And then what we're doing here is basically we do fast inference for the final layer of the network, analytically in closed form. And this is an insight that has been around for a long time, but it actually has sort of been weirdly forgotten in practice, that you can infer the weights of the final layer of a neural network in closed form. And somehow, people know, but they don't do it. Okay, so what we've done here is, in the first 4 or 5 lectures of this class, made our way to how to infer the weights of a neural network if it only has one layer and if the loss is quadratic. And we did that from a completely different direction, motivated philosophically by trying to use the mechanism of inference, the only legally allowed philosophical framework for scientific inference, namely Bayesian inference. And we realized that we had to make all sorts of interesting assumptions that we had to make explicit to keep this philosophical mechanism working, which now actually, in hindsight, motivate a lot of the choices that are being made in other ways, in other sort of perspectives on this field. For us, it was natural to start with a prior because Bayes' theorem requires a prior. And then, therefore, our posterior always existed. Nothing was ever numerically ill-defined. It might have been unstable, but never ill-defined. In a statistical perspective, you might start with just a likelihood. Then you realize that the likelihood might have ill-posed forms, that you might have several possible estimates for W, and then you have to put in a regularizer to do rich regression, and that happens to be exactly our prior. Now, of course, I want to be clear, there are also advantages to this statistical perspective. For example, Matthias Hein on his slide is quickly going to tell you that you will use a different regularizer, the L1 norm, for example. And then you will get the lasso, the sparse form of regression. And then I'll ask you to ask him, what's the corresponding prior? And he'll be like, hey, it's a bit tricky. Go back. OK, so I wanted to make this connection. Now we've made this. And now we can move forward. it would be the naive thing maybe, the most obvious thing to do, not the naive thing, the knee-jerk thing to do now is to say, it's connected to deep learning. Let's go to deep learning. What about what if I had more features, right? If I had, I want to learn the features, what does that correspond to? We'll get to that point because it'll turn out to be actually impossible to do without making very careful approximations. But we can do something else that turns out to be a really beautiful idea that dominated machine learning for more than a decade and has now fallen a little bit along the wayside, but not because it's bad, just because it's so well understood now that there isn't so much research about it anymore. It's still an extremely powerful tool. And that's the idea of, one way to think about it at least, is of making the network ever wider rather than deeper, to add more and more and more features to it until you get to a point where you can actually treat where the features become so regular that you can treat all of them in a finite time, even as their number goes to infinity. That's one way of thinking about it. I'll introduce other names as well. What do I mean by that? Well, so here is a way of approaching this problem from the perspective of code. So I've copied in, again, our sort of template code for regression on functions in a parametric form. So just to remind you, I showed you this exact code already in the last lecture, right? So we can go through this quickly. We're loading some stuff, in particular our Gaussian library that has all this beautiful functionality. Then we define a prior over the weights. We define a feature function. In this case, I decided to use these features that are, give a linear regressor, but you could use different feature functions. We load some data. We condition the prior on this linear observation. And then to make predictions about function values at arbitrary input points, that's the interesting bit. Look at those final four lines. We decide which x we want to compute the prediction on. Remember, we had this plotting grid, right? This lin space. And then we create the features of those input points, phi of x. Then take those features and project our Gaussian distribution, whether it's the prior or the posterior, onto those phi of x to get a new Gaussian distribution, right? So is everyone following along still? This is from last week. OK. So back then, those of you with a computer science background who like functional programming may have already had a bit of an uneasy feeling when I do that, because it seems a bit unnecessarily rigid to do things in this order. So I decide which x I want to project on. Then I create the features, and then I project the distribution. I could also have decided to do this in a more lazy fashion. So now what I'm going to do is I'm going to change the last 4 lines of this code. Everything else is going to stay the exact same. So that's now you know where to put your eyes, right? So I could also have defined a function, a lazy object, that just says, I don't know yet where I want to evaluate, but I can do it anywhere. So I just write down what I will want to do. And then I can hand this object to someone else, to some other function, for example, a plotting tool, and just let it decide where it wants to evaluate. This is a really powerful idea that actually has made a resurgence also in deep learning. In deep learning, this idea is connected to the notion of a neural operator. You may have heard about this. So these are models that are mapping directly into function space. That's the entire idea, right? You just decide not to instantiate the function yet and hand it to the user to decide what to do later on. For example, this structure is used these days in weather forecasting. That you train on data of various resolution, and then you leave it to the user to decide on which mesh to make their weather prediction. And you can do this exactly in this way. You just decide what the mesh is later on. So for us, though, this sort of raises a question. So notice that, so first of all, maybe a question to you. What's the output of this function? I've deliberately left out a type hint. What's the output of this lambda function? Or these 2 different lambda functions? So the prior is a Gaussian. We're mapping it through a linear map. It's a Gaussian. Right? So the output is not a point prediction. It's not a mean. It's not a covariance. It's a Gaussian object. It's a class with all of these different methods. We can evaluate its, posterior mean, posterior covariance, log probability density function, probability density function. We can pick out individual elements and so on and so on. It has all these methods with it. So now you could ask yourself, what is that object then? Right? It's a lazily evaluated Gaussian distribution. It's something that isn't yet a Gaussian distribution, but the moment I call it, it becomes a Gaussian distribution. And maybe it's sort of, since I always have to use the same features here anyway, right? Because I've trained on one set of features and I need to use the same set of features to predict. Otherwise, the whole framework makes no sense. These features should maybe be part of this object, this not quite yet Gaussian object. So here's a slide actually for this. So far, we've used these data classes, Gaussians, that have a mean and a covariance, explicitly instantiated. A vector and a matrix that takes memory footprint, number of parameters, plus number of parameters squared. Right? And then we make these observations, but we actually only care about the function values. Those parameters, they're really just a way of parameterizing the distribution. We could actually care less about these parameters. We want the prediction in function space. I could go on a tangent here on how you could redefine both the features and the weights and get the same model out. So there's even a degree of unidentifiability between what the parameters and what the features are. So maybe what we actually want is an object that is fundamentally function valued and gets only created at the point where I decide where to evaluate it at. So something where these objects become lazily evaluated things, callables, functions that I only call later. You could call this a Gaussian function, but actually it happens to be called a Gaussian process. So for those of you who have had a statistics class, who has heard of Gaussian processes before? Not so many. Okay, interesting. Good. So for those of you who have taken statistics, you've heard about Gaussian processes. You've probably seen them defined in a very, very different way. That's good. Now you get a different perspective. So what we can do here is, or what we're actually doing here is a more specific, so what we've done so far is a more specific version of this abstract design pattern, which is called a Gaussian process. So it's a class that has a mean function and a covariance function, which only get instantiated when you decide that you want them to be instantiated. So I can define such a class, of course, and create a constructor for it without giving it x, and then it just sits around, not using much memory at all. It's just the structure. And then the moment I decide where to instantiate it on, how many x's to think about, it creates these objects. So for that to work, we need to ask one key question. So what are for this to become an actual Gaussian, so for this definition to work, what properties do M and K have to have? So if you think back to the definition of a Gaussian, the definition that I gave at least of a Gaussian is that it's a probability distribution parameterized by a mean vector and a covariance matrix. What did I say about the mean vector? Nothing special. It's just a vector that lives in d-dimensional vector space. What did I say about the covariance matrix? Which property does it have to have? Yes, so it has to be symmetric positive definite or semi-definite for the definition to work out. So if we want this structure to work, we somehow have to make sure that this function here, when we call it, always gives back a symmetric positive definite matrix. Otherwise, we're not defining a Gaussian, and then things can go completely wrong. So we need this function to have this property. Literally, that's the only requirement we have, that when you call it with the same input x on the left and the right-hand side, it creates a matrix a quadratic matrix of size, whatever the shape of X is in its last dimension, square, that is symmetric positive definite. And at first that sounds like a very abstract property, but it's actually the definition of the thing we're trying to construct here. Such functions that have this property that they always return positive definite matrices are called positive definite functions, or Mercer kernels, Mercer functions, or positive definite kernels. Many different names for it. There's a problem that in math the word kernel is completely overloaded. It's used for various different definitions, right? The kernel is also the null space of a map. And so this is a different kernel here. So this word, that's why I'm sometimes going to be calling it a Mercer kernel, gives us a definition for this thing we need. So we need a function that takes pairs of, well, that takes a set of inputs actually. Well, no, more precisely. We need a function k that operates on pairs of inputs from an arbitrary space X and returns real numbers. So that's a scalar valued function which we use in a broadcast-like fashion using this JAX code I showed you to fill the entries in a matrix. And we want to have this function to have the property that if we take a particular finite connection of inputs, n of them, and then broadcast all the possible pairs of these n inputs out to create a square matrix of size n by n, that matrix will always be symmetric, positive, semi-definite. And here's a reminder of what the definition of semi-definite is, but I already asked you and everyone raised their hands and said, yeah, we know what semi-definite means. So if we have such a function, such a kernel, we can define this object called Gaussian process. A Gaussian process is the following thing. So take any arbitrary real-valued function, mu, call it the mean function. Take such a Mercer kernel, such a cool thing, someone gives you this function that makes sure that you always get a positive definite matrix. Then a Gaussian process is a probability distribution over functions mapping from inputs to real numbers, such that every finite restriction to function values, so every instantiation of our lazy function, happens to be a Gaussian object. And here's the definition again. So this is an interesting instance where the code is pretty much exactly the mathematical definition. If you have a k, such that this definition makes sense, so that this satisfies the requirements for sigma being the covariance of a Gaussian distribution, for arbitrary inputs x, then this class is well defined, and then we call this thing a Gaussian process. So a Gaussian process is the functional programming equivalent to a Gaussian distribution. Or maybe it's not the equivalent, but the generalization, the lazy generalization of a Gaussian probability distribution. And even with this, so far I haven't told you how to build something like this, how to make use of it, or whatever. This should just be a definition that excites a computer scientist, right? Because it's a very sort of algorithmically defined thing. It's a function-valued object. OK, now it's 11 o'clock, and we should probably take a break. Quick question. Does anyone have let's maybe for a second reflect. Did everyone get this definition? Because that's usually the most confusing thing. So, yes, question? So good question. So the question is what is this here? So, okay, let's do this in 2 steps. First off, maybe forget about the second colon here for a moment, and just imagine that your x, let's say the x's are just real numbers, right? So we're getting data points like in the example that I did last week, where the x's are just real valued inputs because we're going to do a one-dimensional plot, right? Then this object here there is no third dimension. So we're just going to take the first dimension with a none, and then a none and the first dimension. So this is the JAX or NumPy way of broadcasting. Right? We're just saying, I want this to be a column vector and this to be a row vector, and then JAX is going to broadcast and make a matrix. Now, okay, so that gives a matrix. So now why is there this third dimension? Annoyingly, we might want to use this entire framework on spaces where the x are higher dimensional. Right? So the inputs don't necessarily have to be one-dimensional. Actually, in your homework this week, they're going to be two-dimensional. And so we'll need to be able to deal with collections of data sets where each datum consists of several entries, right? A first feature, a second feature, a third feature, and so on. And that's where we're going to shove those into the final dimension, basically. That's why the third dimension comes from. OK, so maybe that helped. Now let's take our customary 5-minute break, and then we'll be back. Why does this keep breaking? Where's a good point? OK, let's get started again. And I'll go back to the slides for a moment, and I'll show you code now in a second. So, OK, so what we did before the break is I defined this object. And so far, you could think of this like, like in your functional programming class, in like, Thorsten Gruß's Informatik 1, if you studied in Tübingen. You'll have heard of these like abstract objects, and you don't really know what to do with them. It's this super abstract notation. So the question you may now have is, OK, but I mean, what do I do in practice with something like this? Like, how do I actually define such an object? So to do that, we're now going to do two things separately from each other. First, I will remind you that what we've done so far, parametric regression, actually is a special case of this. I'll do that quickly, hopefully. And then we'll realize that we can do something much more powerful that doesn't involve explicitly treating these parameters. So let's first do the first bit. Let me just remind you of what we've done last week, but now with a sort of different perspective on it, focusing on what we do with the input. So last week, because I was focusing on this parameter space, on these weights, on W, I kept talking about W, and the features are just a vector. That's just a vector that comes in. You just create it when you have the X, and then you have this feature vector. Now let's think of this feature vector as the actual operating thing. So I'm going to use this notation with bullets, which is maybe a bit fanciful. I'm just going to keep using it. Yeah, you will get used to it. So you can think of this as as a function that hasn't yet been called. Right? So when there's a bullet, I'm giving a function object that hasn't yet been instantiated. So what we're doing when we're creating our distribution over this f is that we're saying, well, given actually over the data, maybe I should have called this y at input, is that data are going to be Gaussian distributed around a linear map of the weights. So if we want to predict what the function values are, we have to use the sum rule. We have to marginalize out the quantity we don't like. So remember, very first lecture, Kolmogorov's axioms, right? If you want to get rid of a variable you don't care about, you use the sum rule. You marginalize it out. That's what we're doing here. And you get this Gaussian distribution. So now, last week, we focused on mu and sigma, the role of mu and sigma in here. Now let's focus on the role of phi. So phi gets called, it goes into the mean to create the mean prediction, and it goes from the left and the right into the covariance. And because it comes from the left and the right, I'm going to use two different objects here. So you can call this on the left and on the right. But if you want to have a function distribution over the black dot, of course, then the circle and those two are going to be the same, actually. But most generally, to define the objects we need to define these two things. So a function m that takes an input and then computes this inner product, and this kernel, which takes two inputs and then computes this inner product. And these actually have a name in this literature. They're called mean function and covariance function, because they create the covariance of our Gaussian. But we also just realized that this function is a kernel. So it has to be a kernel, otherwise this doesn't work. So far, we've done this operation very explicitly by using these feature vectors. So we took our inputs, our plotting grid, let's call the plotting grid the black dots, and then we created these objects phi, and we multiplied them in wherever was necessary. And we did this with our add operator for our Gaussian distribution. But what I've now been trying to convince you of in the first part of this lecture is, or before the break, is that we could also lift this operation of creating the feature function and instantiating all these matrices. We could lift this into the class, into the Python class that we're using to define this process. Process, literally, pun intended. And define an object that I'm going to call a parametric Gaussian process that just takes care of doing all of this. So a parametric Gaussian process is a particular instance of a Gaussian process using proper inheritance. I promised you object-oriented code. Here it is. It's actually both functional and object-oriented at the same time. Isn't that nice? So that's a proper Python class that inherits this abstract data type Gaussian process. So to inherit it, that means we need to create a constructor that ensures that the interface exists, right? So that's the constructor here. We create it by giving it the feature functions that it's supposed to use and the Gaussian prior that it's going to use as a prior over its weights. And then what it does is it stores these things just for later use, and it creates the things that we actually need for a Gaussian process. So, right, it tells you how to instantiate the Gaussian process infrastructure that we need. And remember that the Gaussian process, again, calls a Gaussian class inside. So now we're already 3 layers deep in our inheritance structure. For that, we need this mean function and the covariance function that are defined here. And they do exactly what you expect. Right? So if I give you an x, then I make the feature functions, I project them onto the mean vector, and I have a mean function. And if you give me 2 x's, I compute the 2 features, left and right, and then multiply them from the left and the right onto the covariance matrix of the prior. There's a squeeze here. Can someone guess why? It's related to the question that you asked before. It's because of this weird broadcasting happening in the Gaussian class here. Because of this, you might get a weird form out in your feature functions, but feature functions are supposed to absorb the x, right? They're supposed to take care of everything that x does. So whatever happens inside should stay inside of phi and not get broadcasted out, which is why we do the squeeze. So, okay, actually, I can show you some code for this. So here, this is also on BDAP Jupyter Hub. You can look at it, lecture 6. Let's hope it just works. So far, this is everything you know from before. I'm just defining features. So I'm loading this data because I want to do regression later. And then I define these feature functions. This time, not the polynomial features, but these Gaussian bumps. Bloop, 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 lots of little Gaussian eggshell-like bumps, right? So this is a bit of a confusing piece of code, but if you stare at it later after the lecture for 5 minutes, you'll understand that it makes this plot that you can see here below. And you have the same problem also. I need to call it twice, and then the error goes away. Nice. So some people complained about my font. Just call the cell twice. The error goes away. I don't know why, but there we go. So here are these features. And as you can see, right, there's actually many features, right? So every little red curve is one of the features. I've just designed them such that they are next to each other. In your homework, you're going to do the same thing in 2D. And then I define a bunch of plotting functions that you can look at later. They're not important. They do the Gaussian plot. Everyone knows what a Gaussian plot is, right? You want a mean, you want a standard deviation, you want samples from the posterior, and you want a shading in the background. You can look at how to do that in matplotlib, but I've just defined it, right? If you have a Gaussian object, you can, of course, define all these plotting things. So now I'm defining this parametric Gaussian process. Can everyone see this cell? Do I need to increase the font size at the back? It's OK? Good. So what I'm doing is I'm saying I want to use 10 features. So that means I'm going to use a prior over those weights, which I instantiate as the default Gaussian. Unit covariance matrix, prior means 0. Of course, that's not going to give us good uncertainty necessarily, but whatever. I'm just going to put it there. And then I say, I want the features phi to be these Gaussian features, and I'm just taking care of instantiating them correctly. Right? I'm just saying, I want these little red shells distributed from -8 to +8, and I want to have 10 of them, and I want their width to be 1, otherwise I could make them narrower or wider. Right? You can play around with this code if you like. But now I have a function that takes in x, and it returns these red curves that you see above. And then I say, please make a Gaussian process that uses these feature functions and this prior. And so far, what computation have I actually done? I've instantiated a 10-dimensional Gaussian. So now there is a unit covariance matrix, and a vector containing 10 zeros has been stored in memory. But the functions are they've just been declared. There's been no call to them yet, which is why evaluating this cell is almost instant. It doesn't do anything, right? So later, I can then say, please make a plot of the corresponding distribution over the function space. Here we go. That was one plot too early. That comes from these features. And you saw that that cell took a second to go, right? It took a little bit of time because it had to instantiate all these things. So they say, oh, OK, what's your plotting grid? Plotting grid has 300 points, so I'm going to have to instantiate a 300-dimensional Gaussian by creating these 300 times 10 features. That creates a matrix that has to go into this mean function and this covariance function, multiply from the left and right. That's why this cell took a bit of time. And now we have this plot. OK, so far, so good. What we now have is a Gaussian distribution that we can call with a bunch of features. But everything we've done so far was just a rearrangement of the computations from last week. Right? So you could say, boring, why are we doing this? Right? We know it's a shallow neural network. Why is this so complicated? Huh? So it's so complicated because this particular design structure, this design pattern of the code, suddenly enables us to do something really cool. One of the most powerful ideas of machine learning in the last 2 decades. Namely, the following insight that I've written down here as this white piece of ribbon in my code, which is that to do these computations, we have to compute the mean function, which is an inner product between the features and a vector. That's actually boring. Quite typically, we can, for example, set the mu to 0, then this function will always be 0. Or remember that the Gaussian can be shifted by an arbitrary mean. So whatever function we put there actually can always be thought of as some mean. It doesn't matter. The mean function is really boring. We can just set it to whatever. But to get this kernel, this positive definite matrix, we need to do this inner product between the features and themselves, weighted by the prior covariance. So kernels, at least these types of kernels, and it turns out that's a general property, it's a non-obvious theorem, kernels can be thought of as inner products. So sums, right? An inner product is a sum. And there are some sums that you can evaluate without instantiating the individual terms. You've encountered them in your undergraduate lectures, in your first year, when you did series expansions and integrals. You basically did sums that have explicit forms that you get without doing the sum. And that means, if we get lucky, we can pick some features that allow us to do inner products over infinite sets of features in finite time. And this idea is called the kernel trick. And it's hugely important in machine learning, not just in machine learning. It's actually been around for a very, very long time in many other fields. But in statistics and machine learning, it became a thing that completely drove the field for over a decade. And it's such an important idea that it's actually, turns out also, it's sort of something that emerged in the second half of the 20th century, maybe even later, maybe like in the 90s, you could say, early 2000s, late 90s, as really a thing. I mean, the main work on it was like in the 80s, early 90s. And that's a time in the world, in the history of science, where it gets increasingly hard to say who did what. So you may be used to, if you take an undergraduate math class, I showed you pictures of Laplace and Gauss, and there are these towering figures. These days, it's more complicated. It's very difficult to point out someone who did something. But the story, the one that people like to tell, involves, for example, these 5 people. So here on the left, you see Grace Waber, the oldest one in the round. She's actually still alive. She's 91 now, and a very sporty person. She was actually in Tübingen about a decade ago. She came by a workshop, cycling on a long cycling tour. She's like a towering figure in the world of statistics. And she introduced a notion called splines, which was the old way of thinking about the kernel trick. I will point her out again on Thursday because she did some really cool stuff that we can directly use. Then the other 4 people are all connected to each other, and they are maybe in the machine learning community most associated with this kernel idea, even though it's difficult to say whether they invented it or whether any one of them invented it, but they happen to be working together at some point. So Vladimir Vapnik is, these days you would say, an Uzbek mathematician. He was born in modern-day Uzbekistan, which was then the Soviet Union. And he moved to the US in 1990, where he started working at Bell Labs. And he worked a lot together with his colleague Alexei Chervonenkis, who was a Russian mathematician, who also worked in London at Royal Holloway. Unfortunately, he's the only one among this group who is not alive anymore. He died in 2014 when he went on a hike, as he was loath to do, in the suburbs of Moscow, and got lost and died of hypothermia. Together, they developed a beautiful theory of the complexity of models you can build with kernels. You may hear about it from Matthias Hein. It's called VC, fittingly, theory, complexity theory, for Vapnik-Chervonenkis. And Vapnik was the PhD advisor to a lot of people, including to Isabelle Bouillon and to Bernard Schurkopf, who together with him developed the classic kernel machine called the support vector machine. If I have time later on, I will talk about the support vector machine in a few weeks, which from the Bayesian perspective is a bit tricky to work with, but it's also still interesting. Isabelle and Bernard both worked on these early versions of the support vector machine. Isabelle Bouillon then stayed in the US, so they were all at Bell Labs together. She stayed in the US for quite a while, working at Berkeley. She also created her own company. She's a super sort of colorful figure, ran a lot of competitions. She's still very important for the world of benchmarks and competitions in machine learning. She's now a professor in Paris-Saclay in France, highly decorated mathematician, computer scientist. And I guess I don't really need to introduce Bernard Schurkopf. Everyone should know him because he's here in Tübingen. He also did his undergraduate in computer science here, so you're in good footsteps. And went on to work at Bell Labs after that, and in Berlin, and many other places, in New York, and lots of things, and is now running the Max Planck Institute here in Tübingen, and is like some outsized, Germany's most cited computer scientist. Okay, and like a father figure to many people in Tübingen. Now, these people together worked on this idea of a kernel, which you now get to experience yourself in one particular explicit case. So what I'm going to do is I'm going to point out one example for today, and then on Thursday we'll find many, many, many more examples. It's not a unique one. It's just one example of how we can construct an inner product over infinitely many features in finite time. Actually, in constant time. And it works as follows. So first of all, let's realize what we're doing here and then create a concrete case. So we need this kernel function, which we've identified with this inner product, right? So keep nodding along if this is obvious, and then I'll go step by step until you stop nodding. This is this inner product over our covariance matrix. I am going to make the specific choice of making the covariance matrix something simple. I'll make it a scalar matrix, so a unit matrix times a number, and that number will be a constant divided by the number of features multiplied by the width over which I distribute these features. So remember in my code that I just showed you, I also had these C min, C max, right? They were -8 and +8. They just say from over which domain the features go. People are still nodding, I can go faster. And I'm going to make the rest of the matrix a diagonal matrix, a unit matrix. That has the nice advantage that this inner product, which now looks like this double sum over I and j over the entries of the matrix, becomes a single sum. Right? Multiplying with a diagonal matrix is easy. It turns a double sum into a single sum. So now we just need to do this. That's what our kernel is. So we have a constant outside that we can play with. We can use it to make things stay nice and convergent. And we have a sum over features. So far, there are finitely many features. And now we can make this observation that there are some sums that you can do in closed form. And here's an example of one that you know from your first-year math lectures. Right? It's a series. And this is an infinite series. It goes from 0 to infinity, but it still has a finite value that you can just evaluate. Right? So here's an example of an equation where I can evaluate an infinite sum in constant time. Question? So why did I pick sigma like this? Which part is confusing? The delta at the end or the stuff in front? The stuff in front. So this is going to be a constant. It just goes in front, and it's just going to be convenient. So I made these choices so that what I'm going to do now will work out. But of course, I can pick whatever number, as long as it's a positive number, right? You can convince yourself that this is a positive number. I make C max larger than C min, so that's a positive number. And then everything stays positive definite. So it's all good. So now let's do an explicit construction, which is due to actually David Mackay, who did this derivation. This is an instance of where if you really want to, you can click on the link up there and see the original paper. So what we're going to do is so I've just copied over stuff. So everything up here is copied over from the previous slide, and now comes something concrete. I will make this choice that the feature functions themselves, the individual ones, are these Gaussian bell-shaped things. So just to remind you, they look like this. Right? I'm going to make exactly this choice. These are the feature functions I'm going to use. And in this case, there are 10 of them. So the sum goes from 1 to 10. And they look like this. So every single one of them is a function of x that has a center at some location, and the centers differ from one feature to the next. And then they have a scale, and there's a number f of them, and that's exactly the situation that you can play with on this Jupyter Hub code that I've uploaded. So this choice is going to be helpful with our computation here, but it's by far not the unique choice. So do not fall into the trap of thinking it's only a Gaussian process if I use these Gaussian features. That's a completely arbitrary choice. It just makes the computation easy. So, OK, let me get rid of the arrow here. So now, if we choose these features, then this inner product, the stuff up here, I'll just put in the explicit forms into these terms here, right? And then we get this expression. So now the equation is quite long, but it's just putting everything in. Nothing has happened yet. And now I look at the stuff inside of the sum, and I say, what I have here is an exponential of a square times an exponential of a square. So what is that? Well, it's the exponential of a sum of squares. And now I can use a property of exponentials of sums of squares, which we've already written down in lecture number 4 on Gaussian distributions. I can use one of the beautiful properties of Gaussian distributions, namely that if you have a sum of squares, you can complete the square. You can rearrange the terms in the squares, right? You can sort of mentally expand all these squares into binomial formulas and then rearrange terms. And then there'll be some terms that depend only on x and not on c, right? Some people have stopped nodding. A little bit of nodding, right? OK, so I can take all the stuff that depends on x and I can move it outside. And you can convince yourself that this is actually this term. And then there's going to be some stuff that depends on c, which will stay inside of the sum because it's different for every term in the sum. Right? This here does not depend on L, the term, the index we are summing over. This stuff depends on L, so I need to leave it inside. The corresponding properties of Gaussians that you can mentally connect this to is the fact that the product of two Gaussian probability density functions is another Gaussian probability density function times a normalization constant. That's exactly what we have here. And now you can maybe guess where this is going, right? So now we have a constant stuff outside. So this here does not depend on the sum. And we just have to get rid of this annoying sum. And to get rid of this, we are going to give it a lot of structure and then take an infinite limit so that it becomes an integral, and then things get easy. So I do this here. Right? I've copied over the last line from the previous slide. That's over here. And now we're going to do several things at once. And here, apologies to the mathematicians in the room. I'm going to be a little bit computer science-y, right? Or maybe physicist, I don't know. And you can just trust me that this works because there's also beautiful theory out there that shows that this actually works and it's functional analysis and it's really complicated and so on. But just suspend disbelief for a moment and follow me along to see that what we're going to do is we're going to increase the number of features. So we'll have more and more and more of these features. And we'll keep them at regular intervals. So I'll keep them at a lint space. Actually, I can do this in the code. Right? I can say instead of 20 features, or instead of 10 features, I'm going to use 30 features. And then everything that changes is just, sorry, takes a second, right? I'll get more and more and more features. And they get scaled down by the number of features, because remember that in front of my normalization constant, I have a 1 over f. So now as f increases, I get more and more and more features. They get linearly narrower. They sort of shrink down. And their distance is regular across the space between -8 and +8. So asymptotically, this becomes a Riemann integral. Right? I sort of asymptotically have a sum here that is, you can think of this term here like a dc, like an infinitesimal sum over dc rather than delta c. Right? Because delta c goes to 0, f goes at the same time to infinity at the same rate, so the two cancel out, and we're just left by the width of the integral, which is exactly this thing. Right? So what we're doing here is basically an integral over this Gaussian function. And now the last thing we do is we just take the integration limits to plus minus infinity, and we make sure that the density of features stays the same. I could do this in code as well, but I don't want to, but you can think about how you would do it. And then asymptotically, this just becomes an integral over a Gaussian function. And here, literally Carl Friedrich Gauss comes to our rescue and says, that's an integral I know. It's the square root of 2 pi. Actually, it's the square root of pi, because I don't have a 1/2 here. So it's just the square root of pi. Done. Just put it there. Scaled by lambda, because of the lambda here. So that's it. So now this infinite sum over infinitely many features is just a function that I can evaluate. And for every pair of xi's, xj, of course, the cost of evaluating this thing is constant. Right? It doesn't scale with the number of features. It already keeps track of infinitely many features. So that means I can define an object here in this line, or in these 3 lines, that creates this abstract thing called a Gaussian process that I had on earlier slides without constructing explicit features directly. And the way I do this is I say, I'm going to use some mean function. Okay, the mean function is trivial. It's just return 0. Just return zeros of the same length as the input. No worries. And then I define this kernel, which is sometimes called the square exponential kernel. Not squared exponential, just square exponential, because there's a square in the exponential. Sometimes it's also called the RBF kernel for radial basis functions, or the Gaussian kernel, because it looks like a Gaussian. That takes in inputs x and y and a bunch of parameters, an output scale and input scale. It returns the exponential of minus x minus y squared divided by L squared divided by 1/2 scaled by the output scale. The 1/2 is not in my definition on the previous slide, but whatever, right? It's just a redefinition of the length scale. And then I say create this abstract data class Gaussian process instead, but if only that now it's not abstract anymore. It's actually a concrete instance. It has this mean function and this covariance function, which I instantiate to some particular output scale and input scale and just say, let's just evaluate. And then I can call this object Gaussian process, and it produces a distribution over function values. And there are no features anymore here, because there are no features. I could not make a plot of features, because there are infinitely many of them, and they are infinitely narrow. So there's no point in showing them. So to do this, I literally use this code that I showed you. So here is this is the code for this week. It's now the complete code for Gaussians. I don't think I'm going to add much more anymore. It's our definition of the Gaussian class that you've already seen. It has all these different methods, all these beautiful properties of Gaussians. There are so many that you sort of stopped caring about them. We've already talked about them a lot. There's all this conditioning and this conditioning with probabilistic linear solvers and so on, and sampling methods and so on and so on and so on, shading, plotting tools, linear algebra stuff, all of this. I'm showing you all of this to point out that we keep using it. It's not gone. It's still there. All these methodologies still available to us. And then at the bottom, there's this new thing called Gaussian process. And that's it. That's the entire new code. We just need to be able to say, let's wrap a functional thing around this Gaussian class. And when we do that, we get this thing that makes a distribution over functions at arbitrary scales with infinitely many features. So now, we're almost done. I could stop here. I actually originally had the slides to stop here. But maybe let me just hint at one last thing we need to think about, which is that this is a prior over function values. How do we condition on finitely many observations? Can we learn infinitely many features from finitely many observations? It turns out yes. I mean, I wouldn't tell you this story if it wouldn't work. We just have to convince ourselves that that's actually true. So let me do this in just 4 minutes, and then I'll get back to it on Thursday, repeat it a bit so that you make sure that we don't forget, that we don't get too confused about it. What does it actually mean to condition a Gaussian process? Well, the thing we have to convince ourselves of is just that the effect of finitely many data points on this infinite dimensional object remains finitely tractable. And so this is actually connected to a theorem in kernel theory called the representer theorem that Bernhard Schölkopf was quite important for, together with Ralf Herbrich and I think Alex Smola as well, which in our Gaussian language looks like this. So remember, so again for us this is going to be quite obvious because we just use the Gaussian mechanism. So just remember the forms of our posterior distribution over the weights and the functions that we introduced, that I had on a few previous slides. So these are just the same equations again. There's nothing new. I just want to point out something. What you can see here is that to make a prediction after having seen data, what is the effect of the data? Well, let's think about it. So here, we need the mean prediction at the training data. That's a finite object, so I can create it at the time I get the data. Then I need the data. That's a finite object. Then I need this matrix, which is the covariance of the data, and that's a finite matrix. It's of size, number of data points by number of data points. I need to instantiate it by calling the kernel, and I can populate the entries in there, but then I just have a matrix. And I can call my linear algebra routine using all the cool stuff we talked about in the previous lectures to do the computation here and get a vector times a matrix gives another vector. And then I need to compute this object. That's the only tricky part. So this is going to be our projection from the data space, which are finitely many, into the function space. And so far, this has been this inner product between the features of the prediction and the features of the observations. So this is actually a rectangular matrix, if you like, which I want to only instantiate by the time I know where I'm going to make my prediction. So I want to call this kernel function not to make a quadratic matrix, but to make a rectangular matrix where the number of rows of the matrix depends on where I want to evaluate. That's why the kernel is defined so that you can take two different inputs. So if I use the notation for the kernels that I've introduced now, then we can rewrite all of this in this sort of more functional language that says the posterior over the function values at the black dots, whatever the black dots are, some inputs to the function, is what we now call a Gaussian process. That's the fanciful notation for this, a Gaussian process over these function values with a mean function that is the original prior mean function, still tractable, plus finite object times this matrix function valued thing that I need to instantiate. And the posterior covariance, that is the prior kernel, still tractable because it's the same thing as before, minus a finite dimensional matrix multiplied from the left and right with function-valued objects that only become instantiated by the time you make the prediction. So when I want to cast this into a computation, I will need to take the data and think about all the finite stuff. And then I can do the finite stuff at train time when I get the data, do the computation. So what do I need to do for that? I need to take the data, compute the prior predictive mean, compute this matrix, do the linear algebra on it. So I'm going to do some matrix decomposition, for example, the Jaworski decomposition, to be able to compute this vector. So that's our call to solve. And maybe a data structure that keeps track of this so that I can do solves later, just like our probabilistic linear solver. And then at the time when someone calls me to make a prediction, a predict time, not a train time, I'm going to instantiate these things and make the prediction. So first of all, the observation is the result of conditioning a Gaussian process on finite amounts of data is another Gaussian process with a new updated posterior mean and covariance function. And on Thursday, I'm going to show you how to do this in code. We're going to have to stare at this, and this code. But it's too long now. I don't want to bore you. I'm just going to show you a picture just to sort of convince you that we can do this. We can do this line. That's what we're going to do. We just say this condition function is inherited from our Gaussian class in some very fanciful way. We need a bit of a wrapper around it. And then we can call them for Gaussian processes just like we can for Gaussian distributions. And it'll make a plot like this, where we have this prior over function spaces, and then return a posterior distribution given data over functions. So this works, and you saw that it ran in finite time, even it ran in less than a second. How to exactly instantiate this in code, this is something that should motivate the computer scientist. We'll talk about that on Thursday. What I wanted to convince you of today is that we can rewrite this parametric regression framework in a functional form. When we do that, we suddenly discover there's an opportunity to use some beautiful math, namely the fact that the objects we need to compute are inner products. Inner products are sums. Sums can sometimes be sped up because there are some sums that you can evaluate in finite time, even though they contain infinitely many terms. When you do that, you get a kernel machine, our first kernel machine, a Gaussian process regression method, which amounts to putting a probability distribution. Remember that there's a difference between distributions and measures and densities. A probability distribution over a space of functions, which we can then work with in finite time. We can condition on finite amounts of data in polynomial time, specifically in cubic time, to get predictions at arbitrary function values at test time, where the prediction cost is actually linear in the number of points we want to predict at. On Thursday, I'm going to get back to that and point out a lot more of the beautiful structure of this framework. I just wanted to get through this piece of code today. And then next Tuesday, we'll do an example. And then next Thursday, you'll hear about a lot of complicated, beautiful theory, because some of the more mathematically inclined here in the room might already be wondering, is there a density function for this? And what does it look like? Is it over an infinite dimensional space? But what if the space is not countable? And how does this work? So we need to think about this. Actually, I'm going to get help for having you tell you about this, because it's a bit tricky and I don't want to get in trouble with the mathematicians in the room. For today, I hope you found this motivating and that you give me some feedback. Thank you very much. I'll see you on Thursday.